Okay. Hello, everyone, and thank you for attending today's webinar titled Grid Interactive Efficient Water Heaters. This session will cover the use of heat pump water heaters to provide a variety of services to the electric grid. An overview of techniques and forecasts of their potential for load shifting will be presented. In addition, methods for controlling heat pump water heaters to best accommodate demand response for both individual units and fleets of units will be presented. Results will be from laboratory testing, field trials, and simulation programs. I'm James Phillips, the moderator for this session. I'm a managing consultant working for Guidehouse, and for the last 6 years, I've consulted with the Department of Energy working on standards and test procedures for consumer water heaters. The presenters for this session are Doug Lindsey from the Electric Power Research Institute, Bethany Sparn from the National Renewable Energy Laboratory, and Josh Blitzbaugh from the Pacific Northwest National Laboratory. Before we begin, I have a few housekeeping announcements. Your screen is customizable. Feel free to make the various windows as large or small as you would like. You can even minimize them to drop the menu at the bottom of your screen. Click through the widgets at the bottom of the screen to be sure you aren't missing any available options. Presentations can be downloaded as PDFs from the resource list in the menu. Attendees are in listen-only mode, but you can submit questions through the Q&A box at any time during the webcast. The presenters will respond to questions throughout and at the end of the presentations. The Q&A can be accessed in the menu at the bottom of your screen if it's not already visible. All presentations will be available for on-demand viewing within a few days on the Engagement Hub. And at the end of the session, we will be opening chat rooms on the Zoom platform for anyone who wishes to continue the conversation regarding the session or to ask further questions of the presenters. To access the Zoom chat, there is a chat room icon on your menu with the link. That's the white box with the people with the thinking caps on. Okay. So on behalf of ACEEE, we wish to first recognize and thank our sponsors for this event. The platinum sponsors are Ream and A.O. Smith. And the silver sponsors are Bradford White, Green Power EMC, Jackson EMC, NIA, and SoCal Gas. So thank you. All right, the first presentation will be from Doug Lindsey. Doug is the Technology Evaluation Area Lead for EPRI's Customer Technologies Program. Doug's work experience includes research on water heating, lighting, and appliances for the applications of energy efficiency, demand response, and efficient electrification. This research primarily involves the evaluation of innovative technologies for inclusion in the integrated grid of the future. Doug currently leads EPRI's Heat Pump Water Heater Collaborative Research and EPRI's Technology Readiness Guide. He's a graduate of the University of Tennessee in electrical engineering. And Doug, you're good to go.
All right, thanks, James, and good morning, good afternoon, everyone. Thanks for joining us on this last session of the Hot Water Forum. I'd like to thank ACEEE for putting on a great event, and I know it was a challenge to shift to virtual only, but I really appreciate the work that they've done, and I know how hard it is to shift an event like this. So thanks for joining us here for the last session. I want to continue the conversation. We've already had a lot of good demand response conversations over the past few weeks. So I want to continue talking about functionality of heat pump water heaters and electric resistance water heaters as flexible resources for the grid. And so let me just jump in and start with what is flexible demand response. This is different from traditional demand response where the focus was just to shed load during peak times. Flexible implies that it can go up or down, and water heaters are a good candidate for this type of demand response. They have the ability to store energy, and loading up and going up and down is something that can be of a benefit in many different ways. Ancillary services are something that traditionally have been performed by generation, but I think in the future, as we move towards a fully renewable grid, that there's going to be a lot of need for flexibility, not just at the generation, but also with end-use loads. And here at EPRI, we're focused on thinking about the future, trying to keep the grid reliable and strong and efficient. And so we're always researching forward-thinking methods and trying to solve problems for the future. I want to talk about a few state and federal initiatives and things that are going on that are related to demand responsive water heaters. Washington State has pushed forward with CTA 2045 being a requirement for water heaters, new water heaters beginning next year. The CEC is actually going to authorize the development of flexible appliance standards, which will be very interesting to see how that goes in the future. Pierre talked yesterday about J13 and what California is doing to try to encourage flexible water heaters that can go up and down and can also store local time of use schedules. So he talked about that some yesterday. And for those of you who don't know, that is an optional criteria right now, but maybe in the future it won't be. And as James referenced, he's been working on the Energy Star connected water heater spec for a while now, and that's in development still. And it's a good effort to document and outline what it looks like to be a demand responsive water heater and how we're gonna verify that. So how are companies doing this today? There's different ways, and these are just a few examples that I have listed on the screen, not to be all inclusive. But there's different methods of doing demand response. CTA 2045 is a communication port that can be plugged directly into a water heater, and it's something that is probably one of the primary methods that we're going to see going forward to incorporate demand responsive commands to a water heater. The water heater receives this message. It could be through OpenADR, it could be through another means. And they interpret this message and can do a load shift or a load shed, a critical peak command, or a grid emergency, even load up. And that's been something that EPRI we've worked on a lot. If you know Chuck Thomas, he's put a lot of effort into this standard, as well as many others here on the call today, probably. And it's come a long way in the past 10 years. Another method for demand response today that currently exists is the proprietary method. I probably should have labeled that middle one proprietary, because it doesn't just have to be Wi-Fi. But some manufacturers have demand response capabilities through a direct to the water heater from their cloud solution, and they can do things like changing the set point and changing the mode of operation, be it efficiency mode or hybrid mode or even electric only mode. Then there's third-party controllers. There's a wide variety of third-party controllers that can be an add-on device to an existing water heater. These have traditionally been for electric resistance water heaters because they're easier to control the electric element, and they can do special functions like ancillary services, frequency regulation, things like that. So here at EPRI, we've tested all of these devices in our lab over the years, and we have a lot of experience with these and are very familiar with them. But I want to talk for a few minutes about what I feel like is the potential for these water heaters. For heat pump water heaters in particular, we've had several presentations this week and last week about some of the pilots that have been ongoing. And I'd like to say that there's some great work that's been done, and it's a great start to these new field deployments of grid interactive water heaters. But I think it's just the beginning, and there's a lot that we can learn from what they've done. Here I'm presenting on the screen what I would say is a more aggressive method to do load shifting, not just peak shaving, but shifting load before and after a peak time period. And here's an example I have here on the green. And this is just an example hourly load shape, not real data, but based on real data. So the green line represents an uncontrolled heat pump water heater on average. And the dotted blue line that I have is an example of how you could do deeper load shifting. And it requires loading up the set point changing from the 125 that most customers have their water heater set at, or 120, loading up before the peak period. And we want to do that efficiently, of course, using the heat pump mode if possible. But you also got to make sure when you have a demand responsive water heater and you want to load up, that you install a mixing valve so that you don't provide a scalding event for the customer. So I would definitely say, as a safety, anytime load up is being used to go above set point, a mixing valve has to be in place. But when you do load up above the set point, you have a lot more capacity than what you typically would have had. And I'm showing an example here of shifting 700 to 1,000 watts. Obviously, every house is different. Larger homes have more ability to shed and shift, whereas 1 or 2 person homes might not have as much ability to shift. But on average, I think there's 700 to 1,000 watt hours available through a 3-hour time period, shifting before and after. And so I've got a load up event followed by a critical peak event. And a critical peak, if you don't know, is more aggressive than load shed in the CTA commands. Or you could do a reduce to the lowest set point, like Rheem has the ability to shift down to 110 as the minimum through their APIs. And so what you want to do is do the most aggressive shed while still allowing the water heater to be able to load up or to provide some energy to not provide a cold water event. But hopefully by loading up before an event, you've provided plenty of capacity for the showers that are going to happen. And then there's a bounce back as you return to normal. So that was a winter example. Here's a summer example for the afternoon peak period. There's less capacity, of course, less load there to shift because we don't use as much hot water in the afternoon or evening. But I'm showing an example where you could save 500 to 800 watt hours. And again, I think these are more aggressive because I've seen some examples from other demonstrations where they just do a load shed command. And with today's programming of the water heaters, that's not enough, in my opinion, to be as meaningful as we possibly can be. And so here's one more example of what you could do with a heat pump water heater. And this is for time of use optimization. And this is a program that I've came up with, and there's probably other ways that you could do it as well. But I've got on the bottom in blue, green, and red an example of a California time of use rate and the different hours where it transitions to a different price. And there's a super off-peak and off-peak, on-peak. This is one example. Every utility in California has different time of use schedules, so you can pick and choose. But this one has 3 different ones. And here I've tried to optimize it for this time of use schedule while helping the grid by doing some valley filling and avoiding the peak in the afternoon as their time of use rate tries to encourage. And by loading up and shifting and doing the critical peak, I'm estimating that this average load, and that's an example, could save about $5 a month, which is up to $60 per year, which could be very beneficial for this customer on this time of use rate. And obviously, not everyone has a time of use rate. Most utilities do not have a time of use rate right now, but in the future, that could change. So let me just spend a few minutes here at the end talking about, actually before I do that, I do want to make a point about this load shape, this green line that I have. I think most of us who have looked at water heaters for a long time know that this is our standard water heating load shape. Peaks in the morning where showers occur. There's another peak in the afternoon. I just want to make a side comment that with COVID, I have a field project that's looking at the hot water usage in an apartment complex. And we've noticed that people that are staying at home all day and not getting up early to take showers and go to work, that the load is completely changed. People are taking showers all throughout the day. There's no normal load shape like we were used to. And it's something that could change permanently in the future if companies decide to stay with people working from home. So just keep that in mind. I'm not going to go into much detail on that, but it's something to think about as we've been used to this typical load shape. And we've put a lot of work around that in trying to think about value for that. It could change in the future, and we need to do more research into what the impacts of COVID and working from home. After COVID's over, people will still be working from home. So what's the load shape's going to change for the home in the future? So in the last few minutes here, I want to talk about Flexible DR, collaborative project that we have here at EPRI. Here's a list of our utilities that are members of this specific project. And our goal here is to advance demand responsive technologies for flexibility. And it's not just for water heaters, but water heaters were some of our projects, and I'll talk about those right here. So we've had one project with SMUD where we looked at preheaters to natural gas water heaters. And this was just an exploratory thing to see what electric resistance heaters could do in terms of grid services. And so I've got a picture on the top right that shows frequency regulation using a Reg D signal. And then on the bottom right, I've got a locational marginal pricing event that we did where the water heater charged. It's a normally off water heater since it was a preheater, but it turned on during times of negative pricing on the LMP. And that's a pretty interesting use case. Today, we don't have wholesale prices down to the end user, but maybe as something, if that happens in the future, this could be a really neat feature to charge a water heater during negative price times. We've also done a project with HECO with 499 electric resistance water heaters with load controllers on them, where we modulated the fleet and did some frequency response there as well, responding to an AGC-like signal, which is that top right picture. And you can see it's very spiky over an 8-hour window, and the water heaters performed very well following that signal. I think it was a 4-second signal. And then on the bottom right, I'm showing several products that we tested that did fast frequency response, where the water heaters would turn off when they locally detect an under frequency event. And that really helps prevent brownouts that are very common in an islanded grid like HECO. We've got upcoming work with SCE, where we're going to do some more work trying to implement flexible heat pump water heaters in the field, trying to do the most innovative and flexible approaches that we can to try to make sure that we can help the grid, but also keep the customer from having cold water events and seeing how that works in the field. So in summary, I just want to wrap up by saying, flexibility is about going up and down. And I think there's a lot of value to doing this. Utilities see a lot of value to this, and electric loads are going to need to be able to be flexible going forward as we move to an all, or as much as we can, a renewable grid. Heat pump water heaters can't shift as much energy as electric resistance because they use a lot less, but I think there's still a lot of opportunity for us to get deeper DR than what some of the current abilities are and some of the current results we've seen from pilots. So I think there's a lot more that we can do with heat pump water heaters still to get more value out of them. And I just want to throw out the discussion question. Maybe we can talk about this more on the Zoom, but it'd be really neat. And I included those electric resistance projects because I think those are functions that we might need in the future. And if we have all heat pump water heaters, we need to be able to control the electric resistance backup element in some of these heat pump water heaters. Certainly we'd have to compensate people for not charging in the most efficient manner, but I think there's value to be gained for both the utility and passed on to the customer to have a more reliable grid if we can provide services with the backup resistance element. So that's something to think about, and be happy to talk with you more after this. But that's all I have for now, and I think I'm going to pass it back to James. Thank you very much.
Thanks, Doug. We are right around 15 minutes for your time. So I think we might want to hold off on answering some of these questions that came through until after everyone's had a chance. The first one from Jessica Atwater from Clear Result might be a quick one to answer. In the graph on the heat pump water heater shift, are you having the heat pump water heater use only its electric elements? Curious as to how the compressor influences the control strategy relative to a standard electric water heater.
Yes, you can control the mode. Well, some of the manufacturers allow you to shift the mode to electric resistance, or to heat pump only. In that example, I was saying heat pump only. When you're operating from 125 to 140, the compressor is not as efficient, and it's going to be running at almost its max wattage, which is, for most water heaters, between 400 and 500 watts. So in that example, I was showing a heat pump charging there.
I think a lot of the rest of these are a little more complicated.
So I think afterwards.
Yeah, we'll move on to the next presentation. So thank you, Doug. The next presentation is from Bethany Sparn. Bethany is a research engineer in the residential buildings group at NREL. Over the course of her 10-year career at NREL, she has been involved in numerous projects involving heat pump water heaters. She has conducted detailed performance mapping of heat pump water heaters, evaluated control of heat pump water heaters through standards like CTA 2045, and run experiments with heat pump water heaters that were controlled as part of a larger whole home strategy. So with that, Bethany, you're good to go.
Great. All right, good morning, good afternoon, everybody. I feel like Doug did a really nice job setting up my presentation, so whoever put the order together did a great job. I'm going to be talking about a project that we did looking at some custom controls that might allow heat pump water heaters to provide more demand response or to ensure better comfort. So just an overview of my presentation. I'm going to touch on the larger project that this was a part of, and then go through the sequence of pieces that we did for this project. So this work was done as part of a larger grid modernization lab consortium project that was funded by Department of Energy. We were just one of the labs involved. Argonne was looking at electric vehicles, and Oak Ridge was focused on commercial refrigeration systems. And each of these three focus areas, ours was electric water heaters, residential. We were all focused on developing standard modeling framework and treating each of those different products as a battery. So developing these battery equivalent models to help with fleet modeling. So how would it look if you had thousands and thousands of water heaters, thousands and thousands of electric vehicles? So there was a lot of focus on modeling in this project, but we needed to do a little bit of lab work to make sure that our models were behaving properly. So the full report of this project, including all three lab work, is just been published this week and is available on NREL's website. I'm going to be today focusing just on the experimental work and just the heat pump water heater portion. Okay, so the first thing we did here was we modified an older GE heat pump water heater. The reason we did this was we wanted to be able to investigate controls for demand response, but we wanted to have a better idea of what was actually happening. This particular water heater did have a port for CTA 2045, but there's always a little bit of ambiguity around what's actually being done in the different modes. So we wanted to have full control for the purposes of reproducing and in modeling. But then we also wanted to take the opportunity to dive into controls a little bit further. Maybe not just look at set point control, maybe we could get into something more exotic like duty cycling. So what we did was we modified this water heater so that it could be receiving controls from a single board computer, in this case, a BeagleBone. So the way we did this is we ripped out the guts. I'm sorry to the people from GE that might be on the phone. We ripped out the guts. We took the relays for the different elements and the compressor and fan and basically decoupled them from the existing control board. And then what these little blue switches in the middle are some relays that allowed us to decide where the control signals for those larger relays were coming from. So either the original GE control board or our own BeagleBone controller. So the process that we went through was we wanted to, as best we could, reproduce the existing controls from the water heater. Anyone that has any experience with heat pump water heaters knows that the performance of each water heater is very dependent on the controls, and each manufacturer does them a little bit differently. So we wanted to, as faithfully as we could, reproduce the GE controls without really, I mean, we didn't know what they were, but we were trying to replicate them so that our initial round of testing would be roughly what we would expect to have happen if we could control the water heater in the set point control fashion. So we ran through lots of different draw profiles with the GE controller, and then we would replicate, we would kind of look at when things turned on and try to implement those on our BeagleBone and then run through the same series of tests. The general framework we had was we were running 24-hour draw profiles and we wanted to match the total energy during that day within 5% with our custom controller. So we did a couple iterations of this. You can see this top graph is some comparison between the two. These solid lines are the custom controls. So the black lines are power and red is external tank temperature. So on the outside of the tank where the manufacturer's temperature would be taken. So solid is our controls, dotted is the original control. So you can see that the phasing, there's a little bit of difference on timing, but the overall energy use was only about 4% different for that day. The draw profile shown below was what we called our medium use, which was actually about 70 gallons, so maybe not quite medium, but this was generated from, NREL has a domestic hot water event schedule generator to develop these sort of randomized draw profiles. So once we were satisfied with how well our controls matched, again, not perfect, but just to give us sort of a reasonable starting place for our controls, we started doing some tests looking at different demand response scenarios. So we had a larger set of scenarios that we wanted to consider, but we whittled it down to just a single load shed case and a single load add case. So for each scenario, we had a base case where the set point was static, so set at 125 the full day. And then we had a basic, I'll start with load shed, a basic load shed test where we had 4 hours where the set point was reduced by 10 degrees F. And then an advanced case where we had a preheating followed by the load shed. And then on the load add side, something similar. We had our basic load add was increasing the set point for 4 hours in the middle of the day. And then the advanced was having a period of time where the set point was lower to try to defer heating until that load add case. I'll mention that we chose the morning load shed instead of maybe what you might expect in terms of a evening or late afternoon load shed because we thought it would be more difficult. You know, we really wanted to investigate these questions of, can you provide load shed in the morning when people are taking showers? You know, I think this is what Doug called his winter case, without affecting comfort. So that we thought that was a little bit more challenging from a performance perspective. I also want to note that we developed these demand response schedules before the Energy Star draft test procedures around connected residential water heaters were released. So we developed these based on time of use rates and other studies looking at control of water heaters, but it might have looked a little different if the Energy Star test procedures had been out then. All right, so here's some results from the load shed case. There's a lot going on here, so I'll move through it slowly. The black lines are all related to our base case where the set point was static. And I'll also apologize for switching into degrees Celsius, but that is what we tend to operate in the lab. So black line and the power measurements down at the bottom, and these lines in the middle are the external tank temperatures again. So black lines are the base case. Red lines are the basic load shed where we're just changing the set point during the load shed period, and then the blue is the advanced case, so where we had the preheating. You'll also notice that there is some green shading, maybe you can see, indicating the preheating period or the load up period, and then the red is the load shed window. So what we see here is that in the case where we did preheating, the heat pump does come on during that period of time and allows it to not turn on at all during the load shed. Even the basic load shed case does not use any energy during the load shed period, but immediately turns on afterwards. The table below kind of summarizes the results. In both load shed cases, energy use does go up, but we completely avoid energy during that 4-hour DR window. But I will note that the minimum outlet temperature, so we're measuring the outlet temperature as draws happen. In the basic load shed case, we dropped down to 36 C, which is about 97 degrees, which is too cold. Our minimum threshold for these tests was 43 C, which is about 110. And that's based on some Building America and Department of Energy literature. So while both cases do avoid energy use during that period, I would say that the basic load shed case doesn't really meet comfort requirements. So same type of graph for load add and same color scheme. So black line is again our static set point. red is our basic load up, and blue is our more advanced load up with the deferred heating. And you can see that the blue case does not do any heating during that 4-hour deferred heating period, whereas the basic load up and the base case do. You'll notice down and below here in our table that we do see a small increase in energy use during that DR window from the basic load add, but a significant increase during from the deferred heating case. But our minimum outlet temperature again drops down to 36 in that more advanced load up case. So it seems like we're deferring heating a little bit too long in this case. So with these results in mind, we use these results to put into some modeling, but we also felt like based on these results, we had, there was some room for improvement. So we looked at some different controls changes that we thought might be helping some of the issues. The issues being maybe hoping to improve the amount of load shifting, whether adding or shedding, and making sure that customer comfort was improved. So some of these control changes are kind of specific to this particular water heater, but I think that the sort of approach makes sense that could be applied to other manufacturers or other sort of control strategies. So the first case was we lowered the, we created a lower element deadband. So this particular water heater, if you exited a shed event and increased the set point temperature, the elements wouldn't necessarily come on. And we felt like we were getting too cold of a tank if the element wasn't coming on in some cases. The second control change was to reduce the heat pump deadband during the shed event. So this is kind of the same idea. We're trying to avoid getting the tank too cold, but we're also trying to avoid using that element. So if the heat pump can come on a little bit faster during a shed event, especially since we've lowered that set point for that shed event, that might help the water heater make it through and provide hot water without having to use the element. The third control change was something we called Super Boost. We were trying to figure out if you could throw anything at this thing, if you really wanted to increase energy use, what could you do? This may not be terribly practical, but we were trying to kind of develop our upper bound on load add capability. So in Super Boost, we were turning the heat pump and the lower element on, reducing the deadband, and increasing the set point to 160, which would obviously require a mixing valve. So this was, load add on steroids. And then the last one was a little bit different. We wanted to look at duty cycling of the compressor. So this might have some adverse effects to longevity of the heat pump, but it would produce a very nice and predictable load shape, especially if you had fleets of water heaters doing this. So I'll just quickly go through some of these results. This is our lower element deadband change. So in all these graphs, the black line is our original controls and the red is the modified controls. So in this case, we have exited a shed event and the temperature set point has gone up by 10 degrees F. In the base case, the heat pump comes on and has to run for a long time. And in the modified controls, the element comes on. And you can see that we get to set point in 30 minutes versus over an hour and a half. Energy use does go up, but that might be preferable to bad comfort results and people leaving the program because of it. This is our changing the heat pump deadband during shed mode case. So again, the black line is our base case and red is the modified controls. We created kind of a really high use drop profile for this, and the red section is where we're in the shed mode with the lower set point. So in the base case, the element comes on, and in the advanced controls, the heat pump comes on first, and eventually the element comes on. But by turning the element on first, we're able to reduce our recovery time, and we keep the demand response period energy down. So that's all shown in that lower table. All right, here's our Super Boost. So this is comparing a load up event with just the set point change versus the load up event with all the controls for Super Boost, which was the compressor plus element plus 160 degree set point. So you can see that power use is much higher and the temperature is obviously a lot higher. So it is successful in increasing energy use as is shown in the table. Not too surprising there. And then the last one is duty cycling. So we started with a about 100 15-degree tank, and we ran through 3 different scenarios kind of in sequence, an hour each. Each of these were a 50% duty cycle. The red line was 10 minutes on each time around, and then blue was 7.5 minutes. Oh, excuse me. Blue was 5, and then green was 7.5. So in the table below, you can see that the total energy for each case is the same, which makes sense. They're all 50% duty cycle. But you can see the delta T, the temperature change over that hour, goes up as the on time goes up. So there was some cases that we looked at that were smaller on times, and you can actually see that the blue, the shortest on time, has these little spikes, so it's a little bit unstable. So the longer the on time, obviously, the more heating you're going to get. So this is something that could be a nice tool for getting a very predictable load shape. So in conclusion, we were not trying to be comprehensive. We know that there's a lot of other interesting control strategies that could be explored, but this was a starting place and a way to get some data to put into simulations so that we could explore this further. I think that there's a lot of other things that could be done that maybe would have better results, both for energy use and demand response and comfort, but this was kind of a starting place. A lot of these control changes would have potentially an adverse effect on the lifetime of the water heater, so that's definitely something to keep in mind. Duty cycling might not be good for the heat pump in the long term. Running super boost at 160 degrees F is also probably not great for the longevity of things and would definitely require a mixing valve. But I think that the takeaway here is that maybe thinking creatively about how controls are implemented during these different events and not just treating the events as changes in set point under normal operation, we might be able to get more demand response potential out of these water heaters and make sure that the consumers are happier with the results. So that's all I got.
Thank you, Bethany. Got 2 questions that I think might be relatively quick to answer. First one is load control switches cannot load up, so I don't think that they can be used for fast response.
We were not looking at fast response. These are all very long, multiple hours events. Whether load up is something that's feasible with existing control strategies out there is maybe a different question, but I think to Doug's point, being able to load up and load shed really improves the performance and the usefulness of these products for demand response.
One more question. Thank you for that. You appear to say that it is okay to cold cock off a heat pump water compressor. I've asked manufacturers and they say that will reduce the life of the water heater compressor. Can you confirm?
Yes, I said that at the end, that cycling the compressor would probably not be great for longevity. Yep, I agree.
All right, cool. And sorry, those were for Doug apparently. So you're welcome, Doug. All right, moving on. The last presentation will be from Josh Blitzbaugh. Josh has performed technology assessment, market research, and economic impact analysis with PNNL since 2014. Prior to joining PNNL, Josh worked on behalf of the California Energy Commission, where he provided strategic planning and technical expertise in support of appliance efficiency standards. Josh has also spent 6 years working on behalf of the Energy Star program, where he developed the first ever Energy Star residential water heater program. So with that, Josh, you're ready to take over.
Thank you, James. I'm going to discuss a method that I developed to forecast the energy use and extrapolate load shifting of grid-connected heat pump water heaters. This analysis was published it's going to be published in 2020 ACEEE summer study. So this presentation won't be able to get into every nook and cranny of the analysis, but you're welcome to check the paper for more information, and I've listed it at the end of the presentation. All right, so water heating is the second largest energy use in U.S. homes, and heat pump water heaters can save 60 to 70% of electric water heating energy compared to electric resistance water heaters. However, right now, market share for heat pump water heaters is low, and so that has sparked some interest in looking for other value propositions for heat pump water heaters. In 2017, a number of organizations in the Pacific Northwest developed a large-scale grid-connected heat pump water heater demonstration study, and this was using grid-connected heat pump water heaters with CTA 2045 standard controls, so a load up, shed, and grid emergency commands. And this study demonstrated that grid-connected heat pump water heaters are an effective resource for shifting load. And a lot of data came out of this study. And so I thought to myself, well, geez, can we put this data to good use, demonstrating other value propositions for heat pump water heaters in other regions? This slide has a heat map that Jeff McGuire of NREL developed from 2012. And I think it's just illustrative of the energy savings potential for heat pump water heaters. And in particular, it shows the energy savings opportunity in the Southeast. And so elaborating on that a little bit, the Southeast and Mid-Atlantic have the highest stock penetration of residential electric water heaters. There's high potential for energy savings. However, utility incentives for heat pump water heaters are relatively sparse right now. On the other hand, utility load shifting programs, demand response programs are relatively common due to peak load costs and grid constraints. So I saw this as an opportunity to demonstrate the viability of heat pump water heaters in providing load shifting in the Southeast, and in particular Florida, which has the highest concentration of electric water heaters. So I spoke with George Gerlaski of Duke Energy Florida, and he was kind enough to work with me on preparing a forecast of energy savings and load shifting potential to the Duke Energy Florida service territory. Duke Energy Florida conducted a grid-connected heat pump water heater pilot in 20 homes in 2016 and has interest in connected heat pump water heaters. It's the second largest utility in Florida, and looking at kind of what I call the sweet spot for heat pump water heater installations, which are single-family homes with a single 30-gallon or greater electric storage water heater and 2 or more bedrooms in the home. There are roughly about 688,000 of these target homes that could convert to a heat pump water heater. And so what I did was I developed a forecast methodology that was originally developed for Duke Energy Florida, but could be repurposed to other regions. And this methodology is a tool to generate momentum for new pilots or programs for utilities. So the methodology takes a look at the energy use as well as the load shifting. Before I start digging into the energy use, I'm going to take a step back and just kind of, at a high level, what I did. So I modeled the energy use for the Pacific Northwest and for Central Florida. And then I took the operating hours and the ratios between Duke Energy Florida modeled operating hours and the Pacific Northwest modeled operating hours, had these ratios, and I used those ratios to apply to the load shifting results from the Pacific Northwest and extrapolate that data to Central Florida to estimate load shifting potential. So to do that, I took some NREL data from lab testing that was based that measured the COPs of heat pump water heaters based on air temperature and average water tank temperature. And when I plotted out that data, there were linear relationships. And so I held the water temp constant at 120 and 90 degrees, and then had it fluctuate based on the wet bulb air temperature. I grabbed the temperature data from Energy Plus using the TMY3 dry bulb and wet bulb temperature data, monthly averages by city, using the cities that were in the Pacific Northwest study and weighting them, and then using the cities for Duke Energy Florida service territory and weighting them based on some weighting factors that George had given me that Duke Energy Florida uses. Then I used an NREL equation from 2007 to take the monthly dry bulb temperatures and estimate inlet water temperature. That's the first equation you see in the slide, and I'm not going to go through every detail of that equation, but I can discuss it afterwards if you're interested. And so the basic assumption that I had was that the air temperature surrounding the water heater was equivalent to the outdoor wet bulb temperature for heat pump water heater COP and the dry bulb temperature for standby loss in the unconditioned spaces. Now for the conditioned spaces, I had used this, you'll see a table at the bottom of the slide, and I had essentially concrete temperatures across the range of months using the wet bulb for the COP and then the dry bulb for the standby losses. And then what I did is I weighted the conditioned space and the unconditioned space in the Pacific Northwest and in Florida, and I'll discuss that in the next slide. So using the COP relationship and the temperature data, I developed a forecast of daily hot water loads, the water heater operating hours, and then the energy use of heat pump water heaters and electric resistance water heaters located in the Pacific Northwest and Duke Energy Florida service territory. So I grabbed the monthly gallons per day numbers from Building America's domestic hot water generator by location, and I weighted them by the locations that I'd weighted using the temperature data. And I ended up with an annual weighted average of 51 gallons per day for Duke Energy Florida and 57 for the Pacific Northwest. And keep this in mind that this is based on that target household profile that I mentioned earlier. I developed the loads using the first equation you see. The first set of brackets is for the daily hot water load, and the second set of brackets are for the standby loss load per month. So that's average day per month. And then I took those loads and converted them to water heater operating hours using that second equation. And then with those operating hours, I multiplied that by the input capacities to develop average energy use per day, multiplied by the number of days per month, then summed over across the entire year for annual energy use for electric resistance water heater and heat pump water heater. And then at the bottom of the slide, you can see the weighting factors I used for unconditioned and conditioned spaces to have a weighted annual energy use number. So that addresses the modeled or forecasted annual energy use, but now I needed to address the load shifting using the Pacific Northwest data. So as I discussed, I developed ratios or adjusting factors to take the data from the Pacific Northwest and apply it to Central Florida. So this is the table of those adjustment factors. You look at month one, which is January, for an unconditioned heat pump water heater, you see 59%. So let's say in the Pacific Northwest, it's 100 watts power draw on an hourly average. You apply that 59%, and you get 59 watts for Central Florida. So that's just a hypothetical example of how those adjustment factors are used for those ratios. Now, the nice part is George was kind enough to pass along some data from a 2010 Duke Energy Florida sub-metering study, which provided some results that we could validate this methodology and compare our baseline to the baseline that Duke Energy Florida measured in 2010. And I'll get to that in slides 9 and 10. So this is the forecasted annual energy use results. You can see in the table, you've got Pacific Northwest, Duke Energy Florida in the 2 rows, and then you've got the electric resistance water heater compared to the heat pump water heater in conditioned and unconditioned spaces, and then weighted in the columns. I think the important takeaway from these modeled results is just that the energy and cost savings are substantial in the two different climates. And if you're looking at an incremental cost of $1,000 to $1,500 for a heat pump water heater, your simple payback will range between 3.8 and 6.5 years. For the heat pump water heater, that's roughly a quarter to half the lifetime of a heat pump water heater. And then for the remaining years that you have that heat pump water heater, you're just putting money in your pocket. That's $230 for Duke Energy Florida service territory, or $260 roughly for the Pacific Northwest. So now getting into the extrapolated load shifting results. In the winter morning, I've got three tables here. The first one is a comparison of the baseline that I forecasted with the Duke Energy Florida 2010 electric resistance water heater data. And I have a row for the percent difference. And as you can see, the hours of 7 to 8 a.m. and 8 to 9 a.m. were the 2 hours that were quite a bit off, 18% and 25%. And I think what that means is just that for those 2 hours, my load reduction numbers may be conservative. So the second table has the forecasted average power demand, but what you may find more interesting is the last table, which is the forecasted average load reduction by hour. In particular, you'll see that the connected heat pump water heater performed the best, which is the bottom row. And then you look at an uncontrolled heat pump water heater versus the connected electric resistance water heater, which underwent events, you can see that they perform kind of similarly, although, you know, there's a kind of a trend you can see with both of them, but on a per hour basis, it was quite similar. And now for the summer evening, same tables. The top is the comparison of our forecasted electric resistance water heater baseline to the Duke Energy Florida 2010 data. We were much closer. The hour at 5 to 6 p.m., we overestimated by 14%. But for the other 4 hourly periods, we were within a single-digit percentage of hitting the data that Duke Energy had measured. The second table has that forecasted average power demand by hour. And then the third one, which I think is the more interesting one, is that average load reduction by hour. And similar story, the connected heat pump water heater performed the best among the three compared to that electric resistance baseline. And then the uncontrolled heat pump water heater and the grid connected electric resistance water heater performed similarly. And now getting to the Central Florida, the case study for Duke Energy Florida. So I took those 688,000 homes that we thought were the sweet spot for heat pump water heaters, and then multiplied my load shifting extrapolated results. And I ended up with forecasted peak load reduction, which are megawatts by hour for the winter morning and summer evening. So you can see in the top table, the hourly average was roughly 270 megawatts reduced for the connected heat pump water heater, and the uncontrolled heat pump water heater and connected electric resistance water heater performed relatively similarly. And for the summer evening, similar story, the grid connected heat pump water heater had an hourly average load reduction of 180 megawatts per hour, and the connected electric resistance water heater and the uncontrolled heat pump water heater performed similarly in terms of reducing load. I also calculated some of the cumulative benefits for Duke Energy Florida residential customers. These are the customers that were in that sweet spot. So those folks would save an annual of 1.2 terawatt hours per year of energy savings, and that's equivalent to roughly 2 billion pounds of greenhouse gas emissions that would be prevented. So there's quite a bit of benefit to those residential customers as well, and Duke Energy Florida would see those peak load reductions that you see in those tables. Sorry for flying through that, but I'm short on time. As you can see here in my last slide, the thank you slide for listening to me, I do have the reference to the paper that provides more detail on this analysis, and I'm happy to take your questions. So James, do we have any questions for this part?
Yes, Josh, there's one question that's come through. Do the cost reduction estimates for the connected heat pump water heater take into account time of use rates?
They do not. So these costs that I show here were just the annual energy savings to the customer. I did a lot of work trying to figure out what the benefit would be to Duke Energy Florida for those peak load reductions, for those megawatt hours in the winter morning and summer peak. And after digging through the Florida Public Service Commission website for quite a bit, I couldn't really get at exactly what those cost savings would be. It was pretty challenging, but if someone has any recommendations as to how to figure out those numbers, I'm all ears.
Maybe that's something we could discuss in the Zoom call afterwards.
Yeah, that'd be great.
Another question, was that 185,000 cars based on the 688,000 water heaters? If not, how many?
Yes, it was. It was based on the. It was based on the energy savings for those 688,000 homes and that's using the EPA calculator. So that's not using the specific fuel mix that Duke Energy Florida had. I'm using a national average there. So it could be different for Duke Energy Florida. I was just trying to put some context around it.
One more for you, Josh. Was the 1.2 terawatt hours energy savings for residential customers and energy consumption saving?
Yeah, so that's the energy savings from the heat pump water heater, but those are not the energy savings from the load shifting. The load shifting, you could total these events because we're looking at really a 4-hour window in the morning and a 5-hour window in the summer evening for what we would consider the load shifting times, the peak times for shift load.
Okay. All right. Looks to be the last of the questions that have come in. We're just about at time. So I guess I'll finish off by saying thank you to our speakers for their presentations and to attendees for participating in today's webcast. Again, if you would like to continue exploring these topics with the presenters, please follow us to the Zoom chat room. Thank you for attending and enjoy the rest of your day. And if you should be able to, the link to the Zoom chat should be popping up. If not, then you can click on the widget at the bottom with the white box with the people with the talking boxes, and hopefully it should pop up. So we'll see you soon.
Thanks, James.
Thanks, James.
See you in a minute.